Okay. Okay, good. So our topics for today will be a new chapter, chapter 4 on Laplace Transform. Okay, so this is our slide for lecture 13. So topics to be covered for lecture 13 are as follows. We're going to have Laplace Transform, number 1. And number 2 will be on the inverse of Laplace Transform. The third one will be on the partial fraction. Okay, partial fraction is a topics I believe that most of you have learned this in mathematics last semester or last 2 semesters, I'm not sure. But I believe that you have learned about partial fraction. So we just have a review, a short review on partial fraction. Because why? Because most of the Laplace transform in terms of inversion from the frequency domain to a time domain will need the use of partial fraction. Okay, so it's very important actually for this chapter, yeah. And number 4, we're going to see the concept of poles and zeros of Laplace transform, in which these concepts of poles and zeros will be usable for us, especially in chapter 5 and 6 later on, chapter 5 and 6. So chapter 5 and 6 basically will be covering the topics of filters. So the filters will need understanding on the poles and zeros of Laplace transform. So it's very important for us to understand what's actually poles and zeros, in Laplace transform. Okay, so let us proceed. So this is the excerpt from the course information. So we're going to learn about the theorems of Laplace transform, the basic understanding. What is Laplace transform is all about, and then also we learned about the inverse of Laplace transform. Okay, and for the rest of these topics, which include the properties and the system characteristics, all of these will be learned later in in lecture 14. Yeah. Okay. Right. So this is the mathematics of Laplace transform. Okay. We have ft. Okay. So ft is a time domain function. Yeah. So we can write that in time domain, if we have ft, we can write the ft or this signal ft in terms of its frequency domain or the s domain, so Laplace transform, and it will become as fs. Okay, so this is Laplace transform. As opposed to what we have learned before in Fourier transform, we have the ft, yeah? So in Fourier transform, we use the f as a symbol for a Fourier transform, and that will give us the f omega, right? Okay, so this is what we have learned previously in chapter 3 on Fourier transform. But for Laplace transform, we have ft time domain. So L is stand for the Laplace transformation, and it is represented by the fs. Yeah? Fs is a symbol for a transformation of the signals in frequency domain. Yeah. Okay, so basically, Laplace transform is quite similar in terms of concept to the Fourier transform, in which it is used to transform a time domain function to a frequency domain function. Yeah, from time domain to frequency domain. Yeah, so that is the purpose of having a Laplace transform and also Fourier transform. Okay, so let's have a look at the mathematics of it. It is given by the integration from 0 to infinite of ft exponential negative st dt, in which the st is a complex, s is a complex number in frequency, and is termed to be s of sigma plus j omega. Yeah. Okay, this is the definition of the Laplace transform. Okay, I want to compare this integration equation with what we have learned, with the things that we have learned in chapter 3 last time on Fourier transform, in which, if we can recall back, the f omega in Fourier transform is equals to integration from negative infinite of positive infinite of f t exponential of negative j omega t dt. Okay, so you can see the comparison, between the mathematical integration that lead to the transformation. Okay, this is for Fourier and this is for Laplace. So the difference is that the f omega, the integration is from negative infinite to positive infinite, yeah? But for the case of Laplace transformation, the integration is from 0 to infinite. So you can see the difference, between the two. So that is why when you go through the literature, yeah, they also mention Laplace transform as a unilateral, unilateral Fourier transform. Okay, because why? Because the Fourier transform, it is covering the time t from negative infinite to positive infinite. But for Laplace transform, it is only covering the positive t value, which is from 0 to infinite, yeah? Right, so it can be said that Laplace transform basically is a subset to this Fourier transform. Okay, Laplace transform is subset to the Fourier transform. So it is quite similar in terms of the concept. Okay. Right. All right. Basically, we can also inverse. Yeah, we can also get back the time domain signal from its Laplace transform signal by using an inverse of Laplace transform, in which it is given by this mathematical equation. Yeah, in which we can get back the ft by simply do the inverse of Laplace transform. Okay, so this is symbol, symbol of inverse Laplace transform of the fs, and this is given by this mathematical equation of this. Yeah. Okay, so as what we have learned in chapter 3 on Fourier transform, we are using a table, right? Using a table for most, or I can say all the transformation that we have learned so far on chapter 3. We just use a table for the transformation. So the same thing is applied for this chapter 4, in which we will be using a table for a transformation, yeah, in which I did provide this attachment in our Google Classroom. This is the attachment that I put in the Google Classroom last time. Okay, so most of the integration, I mean most of the transformation will be based on this table. Yeah, so we have two tables here. We have two attachments here basically. The first one is the properties, okay, and the second one is a functional transformation of Laplace, in which for the second page it is the transformation for respective signal. Yeah, for instance, left hand side here is the signals, ft signals. Okay, we have the step function, we have the delta function, we also have the cosine function and its respective time domain. Sorry, its respective Laplace transformation equation. Yeah. Okay. One thing to be noted here, if we can base on this, yeah, we have all the functions here are having a ut, and most of the functions here are having a ut, right? So this is actually mean that the Laplace transform is only only involve the integration for the positive t value, yeah, positive t value, which is reflected by the integration sign just now, integration range just now. If you can recall back, the integration to obtain the Laplace transformation is from 0 to t. So that is why your signals, all of it are reflected, I mean represented by the step function of ut. Means that all the signals here are meant only for the positive t value. Okay, only for the positive t value. So that is the things that you have to understand, and the difference between the Laplace transform and the Fourier transform. Okay. Okay, so we get back to the lecture 13. Right. So Laplace transform basically is a widely used method in electrical engineering circuit, basically in the circuit analysis, in which if we base on the circuit analysis, if we have a component of passive RL and C, yeah, RL and C. Okay, so our emphasis will be on the L and C, in which we know that the L inductor, the equation that relates the voltage and current for the inductor is given by V equals to L di over dt. And for the capacitor is given by I equals to C dV over dt. And it involves also the integration. Yeah? Let's see, if you want to write the potential V in terms of the current, for instance, the C. Yeah, for a capacitor, if you want to write the V in terms of the current, so this equation will be in the form of integrations, right? Okay, so in time domain, if we base on these equations of R, L, and C, we can say that the solution, I mean the equations of this circuit in time domain will involve a will involve in terms of differential and also integration. Yeah, differential equation. Yeah, will involve the differentiation and also integration. Okay, so in terms of solutions for this equation, which involve the integration and differentiation, will be a lot difficult. Yeah, so it will be very difficult to be solved, very complicated to be solved. So that is why we need to find a simpler method or easier method to solve for this problem. So this is why we need to use a Laplace transform. Because in a Laplace transformation, what we're going to do is that we're going to transform these particular sets of equation which involve the integration and also differentiation into a set of algebraic equations, but in a frequency domain. Okay, so you get the point there, yeah? So we are going to use Laplace transform to transform the equations that involve integration and also differentiation in time domain to a simpler set of equation which is in a algebraic form or algebraic equations, but it is in frequency domain. Okay, so that is the purpose, the usage of Laplace transform, yeah, on this on electrical engineering circuits. Yeah? And the reason for this is that the mathematical operations in algebraic form will be much easier as compared to these integration and differentiation equations. Yeah, so that's the idea. Okay, so basically it's reflected by this case, this diagram. Let's say we have a circuit, yeah, R, L, and C components of your circuit. So the equations for these circuits might involve or can be written in this particular form. Yeah, so we have V over R. We have for the inductor, we can write this particular form, the integrations, yeah, for the V, and also for the capacitor, it can be written in terms of this, yeah, when we want to write the equations in terms of the current, yeah. Right, so this is what we call as integral differential equation, but it involve the integration and also differentiation in your equations, right? So this will be not, this is quite complicated to be solved, and that is why we need to use a Laplace transform, yeah? Right, so this is what I meant, in which if we have the equation in time domain, so a solution in convolutional method will be very difficult. So the alternative that we have is to use the Laplace transform, in which you're going to transfer this integral differential equation into algebraic form. Okay, this is in time domain. So this is in the S domain or the frequency domain. Okay, so I prefer to use S domain. Yeah. So when I say the Laplace transform, when I say Laplace transform, okay, Laplace transform. So it meant S domain. Yeah, it's S domain. Okay, so from time domain, so this will be in the S domain or frequency domain. So we're going to solve it. Yeah, we're going to solve it in a frequency domain. Yeah, so this should be still in the S domain. So we solve the problems in the frequency domain, and afterwards, to find the actual solution, what we have to do is that we have to do the inverse of Laplace transform. So that should be the answer in time domain. So once you have the solution in frequency domain, so you have to do the inverse of Laplace transform, then you can get back the time domain solution. Okay, right. So this is the application of Laplace transform, which will be learned in lecture number 15 later on. Yeah. Okay, so I think we have done with the introduction of Laplace transform, the inverse of Laplace transform, a comparison between Laplace and also the Fourier transform, and then the use, yeah, the application of Laplace transform in electrical engineering. Okay, so now we are going to revisit the partial fraction topics. Yeah, so I believe that all of you have been very, you have learned about the partial fractions before. Okay, so I don't think we have to go this into very much detail. Yeah, so we just go through this part. Yeah. So for instance, if you have your Fs, so this is in the S domain, yeah, in the frequency domain. Let's say the equations is written to be, sorry. Okay. Let's say the equations is written to be in terms of a numerator and denominator. Okay, numerator and denominator, As and over the Bs. Okay, so if we have, let's say, a proper functions, yeah, proper rational functions, let's say we have a case whereby the power of n, yeah, for the numerator is smaller as compared to the power of denominator. N is smaller than the m. Okay, so for this particular case, okay, this is the method of solving the partial fractions. Okay, so for instance, if we have the fs of 2s squared plus 2s minus 6, and the denominator is s plus 1 over s plus 1 times s plus 2 times s plus 4. So if we base on this, we can say that the power of your numerator, which is 2, is smaller as compared to the power of the nominator, which is 3. So for this, we can use this method. So what we have to do is that we have to restructure this fs into a1 over s plus 1 plus a2 over s plus 2 plus a3 over s plus 4. Yeah, so this is a method of partial fractions. So your task is to find what is your a1, what is your a2, and what is your a3. Okay, so I think you have learned this very much in mathematics. So we just proceed further. So in order to find the a1, what we have to do is that we have to multiply both sides with the s plus 1. So end up, we have to substitute s equals to -1. So we can find a1 equals to -2. Okay. Then to find the a2, we have to multiply both sides with s plus 2. Okay, so we're going to have this equation. And to find the a2, we need to substitute s of -2. So you can find the a2 equals to 1. Yeah, the same things apply for us to find the a3. Yeah, we need to multiply both sides with s plus 4. So we're going to have this equation. And afterwards, to find the a3, we need to substitute both sides with s of -4, and you can find the a3 equals to 3. So once you have the a1, a2, and a3, so you can then say that the partial fraction for this fs will be in this particular form. Yeah. Okay, so that should be the partial fractions method lah. Yeah. It's very straightforward. Okay, so that is for the first case where we have a proper rational function. And for the second case where we have improper rational function, where the power of your numerator is bigger than the power of your denominator. So what we have to do is that we have to do the long division first. Yeah, long division operation. That should be the first thing to be done. For instance, for this particular fs, the power of numerator is 4 and denominator is 2. So have to do the long division operation. And when you do the long division operation, you're going to get this equation down here. So we're going to have s squared plus 4s plus 10 plus this terms is now written in a proper rational function. So for these solutions, we can use the method that we have learned in the previous slide. Okay, so that are two conditions that we are going to meet in solving or in writing the functions into its partial fractions. Yeah. Okay, so I think we have done it with the partial fractions. We just revisit it to ensure that you can recall the things that we have learned before in mathematics, because as what I've mentioned you in the earlier parts of this lecture, you are going to meet or you're going to use these partial fractions most of the time, yeah, in Laplace transform. Okay, then this will be the last topic for lecture 13, which is to understand the poles and zeros concept of Laplace transform. Right, so let's say we have the Laplace transform of fs is given by this. Okay, so the fs, we have the numerator part and also the denominator part down here. Okay, so for the numerator polynomial, yeah, numerator polynomial, the roots of this polynomial is called the zeros. Yeah, the roots is called the zeros. Okay, for instance, for this particular polynomial, the roots are -z1, -z2, -z3, and so on. So these roots are called the zeros. Whereas for the denominator, the roots of this polynomial are -p1, -p2, -p3, up to -pn. So all of these roots are called the poles. Yeah. So zeros are the roots for the numerator. Poles are the roots for the denominator. Yeah, for your Laplace transform terms. Yeah, the fs. Okay, this is very important because later on, when we learn about the filters in chapter 5 and 6, we are going to learn about the zeros and poles concept of your transfer function. Okay, So this is the example, just to make sure you understand the concept of zeros and poles. So for the case of fs here, you need to find the zeros and poles for this rational function. So simply we have for the zeros, for the zeros it is equals to -2, +1, and for the poles we have -3, +5, and -4. Okay, so this is the zeros and poles for your fs. Okay, is it understood? Any question on this lecture 13 so far?
No.
No. Okay, very good. So I think we have done lecture 13 and we can now proceed with lecture 14, which is on these topics on the properties of Laplace transform. So two properties will be learned. The first one will be on the functional and the second one will be on the operational properties of Laplace transform. Yeah. Okay, so let us proceed now with lecture 14. All right. Right, so lecture 14, the topics will be on the properties of Laplace transform. So we are going to use this table most of the time. Okay, this table most of the time will be used. So make sure that you have this attachment with you. You need to have a copy to ensure that you understand it. I mean, you can use it straight away in this lecture. Right, so this will be the excerpt for lecture 14, in which we are going to learn about the properties of Laplace transform. Okay. All right. This is the functional transformation. Okay, let's refer to this attachment, page number 2. Okay, so all of these are the transformation pair for respective signals in time domain, right? So if delta t is 1, ut is 1 over s, yeah, for instance, yeah, cos omega t is s over s squared plus omega squared, and so on. Okay, so please be noted that in this particular attachment, for the case of Laplace transform, we don't have any sorts of rectangular functions. Remember, yeah, rectangular functions that we have in a Fourier transform last time. Yeah, for Fourier transform, we have a rectangular functions, we have a triangular functions. Yeah, but for the Laplace transform, we don't have it. So we are just given this kind of a signal. Yeah, but yeah, for instance, if we consider rectangular functions, yeah, let's say, sorry. Okay, for instance, if we have rectangular functions, let's say we have functions like this, rectangular functions, yeah, let's say this is from -1 to +1, instead of 1. Okay, this is a rectangular of t divided by 2. Okay, so in terms of, these rectangular functions can also be written as ut plus 1 minus ut minus 1. Okay, so we can write these rectangular functions in terms of these step functions, and we can proceed with this table to find the Laplace transform for these particular rectangular functions. Okay, so these are the things that you have to understand. Yeah, because obviously from this table we don't have any similar functions that we have previously in Fourier transform. So we need to do some modifications to those functions, so to ensure that we can write those functions. We can write those functions in the form of available functions here in this table. Yeah. All right. Okay. So you can refer to this table on the functional transform. Yeah. Right. So our interest will be on this operational transform, which is basically on the first page of this attachment. Okay, so that will be the main topics to be covered in lecture 14, in which we're going to cover all of these properties, yeah, from linearity up to the final value theorem. Okay, so this will be covered in lecture 14, yeah. Right, so we have few properties here, so we're going to cover this one by one, yeah, starting from linearity. Okay, so let's have a look here. We have a linearity properties, right? So these properties state that if we have the functions in time domain of ft. Okay, so we know that in Laplace transform, this can be written as fs, right? So if we have a multiplication with a constant, let's say a of ft So its Laplace transform will simply a similar multiplication, which is will be A of Fs. Okay, so this is a properties of linearity, yeah? Okay, so that's done. The second properties will be the addition and subtraction, in which if we have addition of the functions in time domain, for instance, if you have A, ft plus b of xt, so in frequency domain or in the S domain, it will be the A of fs plus the b of xs. Okay, so aft, the Laplace is A of fs, the bxt, the Laplace is bxs. So the addition in time domain will result in the addition in frequency domain. So the same things happen for the subtraction. So the subtraction in time domain will result in the same subtraction in the frequency domain. Yeah. Okay. So this is the properties of addition and subtraction. Right. So let's have a look at the first example here, where we are given the ft in time domain of 3 over 2 of exponential 3t minus 3 over 2 of et. So we need to find the transformation, Laplace transformation for this particular signal. Okay, so for this, you have to refer to this attachment table to find the Laplace transform for the exponential of 3t. Okay, so when we refer to the attachment, okay, we refer to the second page. We can notice that for the signal number 6 here, yeah, we can write that if you have exponential negative et ut, the Laplace will be as 1 over s plus a. Which means that if we have exponential of positive et ut, so the Laplace of it will be 1 over s minus a, yeah? Okay, so the same things apply. We're going to apply this concept into this solution. Okay, it's understood here that in in Laplace transformation, all of this function in time domain here is only valid for time t bigger than 0. Yeah, then only for time t bigger than 0. So that is the specific understanding in which the Laplace transform is only applicable for the case of t bigger than 0. Yeah, so you have to understand that clearly. Right, so for that, if we have a functions of 3 over 2 of exponential 3t, the Laplace of it will be equals to 3 over 2 exponential of negative 3t. Sorry, I apologize. Sorry, my mistake here. It's my mistakes. Yeah, sorry for that. Okay, so back to this, we have EAT going to have 1 over s minus a, right? So we're going to apply that. So that will be written as 3 over 2. Okay, 3 over 2 over s plus 3. Okay, right? S or minus, minus or plus? Let me see. Let me check again. Oh, sorry, it should be negative. I apologize. It should be negative. Okay, it should be negative. Yeah, sorry for that. So that should be negative 3, yeah? Okay, the same things apply if we have 3 over 2 exponential t. So the Laplace for that will be equals to 3 over 2 over s minus 1. Okay, yeah? So the subtraction will result on the same subtraction in the S domain. So it should be, the Laplace transform for that will be 3 over 2 s minus 3 minus 3 over 2 of s minus 1. And if you solve for that, your answer will be obtained as here. Yeah, as so it should be the same, right? Yeah. So solve for that, you're going to have this formula of fs. Yeah. Okay. So hopefully you understand about these properties, linearity and also subtraction. You can ask me any questions, yeah, within the lectures, no problem. Okay. Number 2, we're going to have we're going to learn about the properties of time shifting and also time scaling. Okay, for the time shifting, if we have ft in time domain, so let's say in Laplace it is fs. So if ft experience a shifting of a constant, yeah, so Laplace for it will be simply exponential negative as of fs. And the same happens if we have a positive shifting t plus a, the Laplace will be exponential of as of fs. Okay, so that should be the properties of time shifting. Right? Right, so let's have a look at the solution for this example number 1. So we are given the Laplace transform for the signal here, where the ft equals to 1 from 3 to 4. So we can sketch it to be look like this, okay, which is from 3 to 4 instead of 1. Okay, so we can write this in terms of ut minus 3 minus ut minus 4, right? So what we can do, sorry, I can write this is ft, yeah. So we need to do the Laplace transformation as requested from the question. The Laplace for this will be equals to fs, and that will be equals to 1 over s exponential negative 3s, okay, and minus 1 over s exponential negative 4s. Because why? Because we know that if you have ut, so the Laplace of r it will be 1 over s. This is from the table, yeah. Refer to the table now. This is ut here. Okay, ut, this is 1 over s. Okay, if ut in the Laplace, the s domain will be 1 over s. So the same things applied here. Okay, so basically it's a ut. So Laplace for it will be 1 over s. So when we have a shifting, which is ut minus 3, so the results will be 1 over s exponential negative 3s. Yeah, so same things applied for ut minus 4. So we substitute, I mean, this is the answer for the Laplace transform for the given ft. Okay. Any question for this example? It's quite straightforward. No, yeah? All right. So let's have a look for the second. Next properties will be on the time scaling. So you have AT. AT means the time scaling properties. Okay. So the Laplace transform for it will be simply 1 over A, Fs over A. Yeah. So that should be a Laplace transform for the FAT, which is a ft experience the time scaling of A. Yeah. Right. Next will be the frequency shifting properties. Yeah. Where if we have ft, yeah, that ft will give us Laplace of it will be fs. So if we have a multiplication of ft with the exponential function, let's say at, so this will result on the shifting of frequency. So that will result on the fs minus a. Yeah, and if we have exponential of negative at of 8 ft, so the results will be fs plus a. Yeah, so this is a properties of frequency shifting. Yeah. Okay, so for instance, let us proceed with these examples here, where we have ut minus 3 minus ut minus 4 multiplied with exponential of 2t. Okay, so we need to find Laplace transform for these ft terms. So we know that if we go to the basic, yeah, so ut function, the Laplace for it will be equals to 1 over s. Okay, we have understand this. Yeah, so we now proceed to the time shifting. So ut minus 3, we are going to have the Laplace of it will be 1 over s exponential negative 3s. Okay. And now if we have multiplication with exponential terms, now it is exponential of 2t. The Laplace for it will be resulted on the frequency shifting, where all the s terms here shall be shifted. Yeah, so we're going to have what? Going to have 1 over s minus 2 exponential negative 3 of s minus 2. Yeah, and the same things apply for ut minus 4 exponential 2t. The result for that will be 1 over s minus 2 exponential negative 4 s minus 2. Okay, so that's why we have the fs as given here. All right. Is it clear? Okay, yeah. Okay, next properties will be a time transformation, which is a scaling and a shifting that exists in your transformation, in your signal. Yeah, so in this particular case, you have signals of A t minus b, which is a combination of shifting and scaling of time. So if we face with this kind of signal in time domain, so its frequency domain or the s domain will be simply 1 over a, fs over a exponential negative sb over a, yeah? Okay, then. Right, so next properties will be on modulation. Okay, so similar to what we have seen before in chapter 3, that any functions that said to be multiplied with the trigonometric function, cosine or sine, so that will be a modulation, yeah, modulation property. So it's given by this, okay, you can refer to the table, yeah, that the xt, I mean the transformation for the xt cos omega t shall be written as this, yeah. Okay, so I'm going to go into detail for that properties. So for convolution, yeah, convolution is the next properties to be covered. Right, so we know that um, in frequency, in time domain, if we have two signals that are said to be convolved, yeah, ft convolved with the gt, so in frequency domain, it will be a multiplication. So similar to what we have learned before in in chapter 3, yeah, right? So in time domain, if it is a convolution, so in frequency domain, simply it is a multiplication of the functions, yeah. Okay, so let's have a look at this example here. We are given that the xt is ut minus 1. So the question is to find a self-convolution, yeah, to find a self-convolution for the xt. So what should be the result of self-convolution for the xt? Means that we need to find out what is the xt convolved with xt. Okay, that's what's meant by this question, yeah? This is to find the self-convolution. Okay, so we know that given here that the xt is ut minus 1. So in terms of a Laplace transformation, okay, it is given by, or it will be equals to xs equals to 1 over s minus 1 over s exponential of negative s. Okay, so this is the Laplace transform for this xt. Okay, so we know that if we have in time domain a convolution, so in Laplace transform or in the s domain, it should be a multiplication where it should be xs multiplied with the xs. So we're going to have 1 over s minus 1 over s exponential negative s multiply with 1 over s minus 1 over s exponential negative s, yeah? Okay, so that will result on 1 over s squared, okay, minus 2 over s squared exponential negative s plus 1 over s squared exponential negative 2s. Yeah, negative 2s, sorry, negative exponential negative 2s. So this will be the results of self-convolution, but this is written in frequency domain. So what is meant by this example is the results of self-convolution in time domain. So what you have to do is that you have to do the inverse of Laplace transform to find the solution for these particular terms. Okay, so you have to do the inverse for these three terms here. So we know that from the table for this attachment, yeah, if you can refer to the attachment here, that if we have a functions of Tn of ut, so we're going to have n divided by s to the power of n plus 1. So if we have, for instance, t squared of ut, the Laplace for it should be equals to 1 over s squared. Sorry, yeah, sorry, my apologies, my mistake, yeah. It is not t squared, it is t, yeah. It is t. Okay,
Doctor,
so if you have t,
do we need to simplify it?
come again?
Do we need to simplify it, Doctor? Because simplify it,
Which
or we
one?
can just leave it.
Which one
Anyone,
was it?
any equation. Do we need to simplify it to the last form, or we can just do the Laplace in
Do you mean this question just now or which one?
Yes, yes, the last one, Doctor.
Okay, this is not yet done.
No, no,
Not yet.
the one in the right.
This one, is it?
No, the one in the right.
Here, is it?
Yes.
Okay, this is the XS. So you don't have to simplify because this is the actual equation. So we cannot simplify it anymore. Yeah, so you have to use it. Yeah, so you have to use this XS, which is obtained from the Laplace transformation of this XT. Okay, then yeah. So what we are doing here is that we are multiplying both XS and it come out that we are getting these equations here. Yeah, we have three terms that we have obtained. But the next step now is to find the inverse of Laplace transform. So we need to do the inverse for these three terms. So that's why I need to find out. I'm going to use a table to find the inverse of Laplace transform. Yeah. So that's why I'm referring to the signal number 5 that if we have t of ut or t functions, yeah, t ut, so Laplace for it will be simply equals to 1 over s squared. So we're going back to this lecture 14 now, in which if we have 1 over s squared as the s domain signal, so the inverse of it shall be equals to t of ut. Okay, yeah, so you got the point there, yeah? Okay, that's why for the inverse of this, we're going to have t of ut for the first terms. For the second terms, you are going to get 2 over, sorry, I apologize, yeah, it's my mistake, it's not 2 over. You're going to get you're going to get 2t minus 1 of ut minus 1. Okay, why we have this? Because remember that if we have t ut, the Laplace for it will be equals to 1 over s squared. Yeah. So if we consider that the t or the time domain function is said to experience a shifting by 1 unit, so we're going to have t minus 1 ut minus 1. So Laplace for it will be equals to 1 over s squared exponential negative s. Okay, so this is from the shifting properties that we have learned in the earlier part of lecture 14. Yeah, the same things apply. And for the third terms here, again, you're going to have t plus 2, okay, sorry, t minus 2. Yeah. Okay, because we have a negative 2s there. So t minus 2 ut minus 2. Okay, so that should be the answer for this self-convolution for the xt, in which you're going to have the answer is tut for the first inverse of Laplace. Then we have 2t minus 1 ut minus 1, and then we have t minus 2 ut minus. So that should be the answer for the self-convolution of the xt. Okay then. Any question for these properties of convolution? No, yeah? Okay, so let us proceed with this example here. Okay, this is a sample of past year's questions that involve a Laplace transformation. Okay, so we are given the xt signal, which is a rectangular function. The range is from negative half to positive half. This is positive half, yeah? And the signal xt is now being the input to the system, where it is written that the system is h1t and is equals to xt plus 2, and the output is y1t. Okay, so based on this, you are requested to determine the mathematical expression for the y1s and also the y1t, in which we need to find what should be the s domain, so the s transform for the y1t, okay, and also need to find what should be the y1t, yeah, the expression for it. Okay, so based on this, we know that the relationship between the input xt, the system h1t, and the output y1t can be written as y1t shall be equals to the input xt convolved with the h1t, right? So that should be the relationship between the input, the system equation, or the system transfer function, and also the output of y1t. Okay, so this involves a convolution. So the question is to find the y1t and also the y1s. So we know that since this is a convolution, yeah, so what we have to do is that we have to apply the properties of convolution for the Laplace transform, in which when we do the Laplace transformation, it will result on the multiplication of both xs and h1s, in which we're going to have y1s shall be equals to xs multiplied with h1 of s. Yeah, simply a multiplication. And from what, so for this particular case, we need to know what is the xs and what is the h1s. Okay, so that should be our task now, which is to find the xs and also the h1s. So from this diagram, we know that the xt can be written as ut plus half minus ut minus half. Am I right? Yeah, so for Laplace transform for the xt, we're going to have the xs shall be equals to 1 over s exponential negative s over 2, okay, s over 2, okay, and minus 1 over s exponential negative s over 2. Okay, that should be the Laplace transform for the xt, yeah, based on the equations here. Whereas for the h1t, we know that from the equations given that h1t equals to xt plus 2, yeah, so h1t is equals to xt plus 2, in which it can be written as ut plus 5 over 2 minus ut plus 3 over 2. Okay, so the Laplace transform for the h1t, which is h1s, shall be equals to 1 over s exponential 5s over 2 minus 1 over s exponential 3s over 2. So that should be the h1s, yeah, which is a transform or Laplace transform for the h1t. Okay, any question up to now? No, yeah? Right, so if there's no questions, we can then simply multiply both s domain terms, xs and h1s. So we need to have 1 over s exponential s over 2 minus 1 over s exponential negative s over 2. Okay, multiply with 1 over s exponential 5s over 2 minus 1 over s exponential 3s over 2. Okay, so we're going to solve this multiplication. So end up, supposedly, you're going to have the ys shall be equals to 1 over s squared exponential of 3s minus 2 over s squared exponential of 2s plus 1 over s squared exponential of s. Okay, so that should be your ys, y1s, sorry, yeah, y1s. y1s. Okay, but we are yet to find the y1t, yeah? So what we have here is just the y1s. So to find the y1t, what we have to do, we have to do the inverse of Laplace transform. So now we need to do the inverse of Laplace transform. So we're going to have the y1t. Okay, so we know that this will be in a form of t, yeah, t squared, oh sorry, tut, and we have the shifting. So that should be written as t plus 3 of ut plus 3. Okay, that should be the inverse of Laplace for the first term. The second term, so it should be 2 of t plus 2, yeah, ut plus 2. While for the third terms here, since we have exponential of s, so it should be plus t plus 1 ut plus 1. So that should be your y1t in time domain. Okay, any question for this y1t? The inverse from y1s? No? No questions, yeah? Okay, let's proceed further. So this should be the properties of differentiation. Okay. So you can refer to the table on these properties. So in general, if we have in time domain, which is ft, So it should be, the Laplace of it should be equals to the Fs, kan? So if we have differentiation of the Ft, for instance, we have n order, yeah? So this is given to be in n order. So that should be the equations, or that should be the Laplace transformation for the n order differentiation of the Ft. But for our case, we're going to, our interest will only up to the second order of differentiation. So we have the first order, and that should be the second order. Yeah. So for the first order, so it should be when we differentiate for the first order of Ft, so Laplace of it will be S of Fs minus F0, in which F0 here means it is Ft at t equals to 0. Yeah. Whereas for second order differentiation for the Ft, okay, so it should be, the Laplace of it should be S squared of Fs minus Sf0. This is Ft at t equals to 0, minus df0 dt. So this is the f prime t, or the first order differentiation for the Ft at t equals to 0. Okay, so our interest will be only on two equations, yeah, which is first order differentiation and second order differentiation. Okay, right. So let's have a look at this example in which we're going to test our understanding on these differentiation properties of Laplace transform. So for this example, we are given equation, which is a differential equation, yeah, y double prime plus 6y prime plus 5y equals to 2, where we are given the y0 of 1 and y prime 0 of negative 3. So the question is to find the yt, yeah, find the yt. So it is easier for us to do the Laplace transformation for these problems, yeah, because it will be easier for us to solve it. Okay, so what we have to do is that we have to do the Laplace transformation, in which if we do the Laplace transform, yeah, Laplace transform, we're going to have s squared of ys minus s of y0 minus y prime 0, y prime 0. This is for the first term, yeah, plus 6 of s ys, okay, minus y0. So that should be for the second terms, okay, y prime t, plus 5, okay, for the yt, going to have only ys in Laplace transformation. Whereas for the 2, okay, for this particular 2, so 2 here means 2ut, yeah, 2ut, okay, 2ut. So for this 2ut, the Laplace transform for it will be equals to 2 divided by s. So that what we're having here is the Laplace transformation for the time domain equations given in the problems here. Okay, so what we have to do now is that we have to rewrite the equation in which we want to find the ys basically. So when we write it here, so we're going to have ys is taken out. Yeah, we take out the ys, and we're going to have it as s squared plus 6s plus 5. Okay, we factor out the ys. Okay, and we're going to have 2 over s, and the rest of terms, which is the s and this y0 and y prime 0, all of it can be bring to the right hand side. Okay, so we're going to have plus s and plus 3, so you can work out on your own, yeah, on these equations. Okay, so end up we're going to have ys shall be equals to 3s. Okay, sorry, I apologize. Okay, sorry. So we're going to have s squared, okay, plus 3s plus 2, okay, divided by 2 divided by s, yeah. Divided by s, okay, that should be the s, and you're going to have s squared plus 6s plus 5. So we can rewrite this as equals to s squared plus 3s plus 2 divided by s plus 1, and s plus 5. Okay, so that should be your ys lah. Okay, so what you have to do now, remember we have to find what? We have to find the yt, right? So what we have here is the ys. So to find the yt, we need to do the inverse of Laplace transform. But before we can do that, we need to write this ys in terms of partial fraction. Okay, partial fraction. So we need to do the partial fraction for the ys. So ys can be further written as a over s plus b over s plus 1 plus c over s plus 5. So your task is to find what should be the a value, what should be the b value, what should be the c value. Okay then. Okay, so by right, we can work out on this, in which the ys shall be equals to a will be equals to 2 over 5. Yeah, so 2 over 5s. The b will be 0. Yeah, b will be 0, so we can ignore the b. And c will be equals to 3 over 5, so we're going to have 3 over 5 of s plus 5. Okay then. Okay, so this is your ys, in which from here we can write or we can do the inverse of Laplace transform. Yeah, so this is your ys. So your task is to now do the inverse of Laplace transform. So you're going to have your yt shall be equals to 2 over 5 of ut, okay, plus 3 over 5. So since we have here is s plus 5, right? So this involves the frequency shifting. So we're going to have exponential of negative 5t of ut. Yeah, this is 3 over 5, yeah? Exponential negative 5t of ut. Okay, so that should be your yt. Yeah? So any questions for this example? Any questions so far? No, yeah? Alright, no question. Let's proceed further with the next properties, which is the integration. Okay, so for the integration, we can say that if we have a function ft, which is having the integration from 0 to t, so if we do the Laplace transformation for this integration, integrated function, so your Laplace will be simply fs divided by s, in which if the ft is fs in terms of its s domain transformation, so the integration for the ft, which is said to be integrated from 0 to t, will result on this Laplace transformation, which is fs divided by s. Yeah. Okay. So let's have a look at this example here. We are given equations of 2at plus 3 plus integration ax dx over 0.1 equals to 4 exponential negative t ut. Yeah. Okay, so the question is to find the at, right? So what we have to do is that we have to transform this into Laplace. Yeah, into Laplace. So we're going to have 2 of as plus 3 over s, yeah, because your 3 here is considered to be 3 ut. This is 3 ut. So when we do the Laplace transform, we're going to have 3 over s, yeah, 3 over s. Okay, plus 10. So that will be equals to as divided by s, yeah, because this is integration. So when we do the Laplace transform, it should be as over s, yeah. And for this, we're going to have a 4 over s plus 1, yeah, over s plus 1, because it involves the frequency shifting, yeah. Okay, so we need to rearrange the equations here, yeah. So we factor out the as. We're going to have as, okay, as, so that will be 2 plus 10 over s, okay, and then we have 4 over s plus 1 minus 3, yeah, minus 3 over s, okay. So we're going to have AS shall be equals to 4S minus 3S minus 3 divided by let me see. Okay, okay, let me rewrite this. Sorry, I think it's my mistake. Sorry for that. Okay, I'm going to bring it down here. We're going to have more spaces here. So AS of 2S plus 10 over S equals to 4S minus 3S minus 3 divided by S plus 1, yeah? Okay, this may cancel out. So we're going to have AS shall be equals to S minus 3 divided by S plus 1 and 2S plus 10. Okay, so that should be the AS, yeah? So you have the AS as equals to S minus 3 divided by S plus 1 to S plus 10. So what you have to do now is that you need to find the AT, kan? So to find the AT, you have to do the inverse of Laplace transform for this AS. But first of all, before you can proceed with the inverse of Laplace transform, you need to do the partial fraction first, yeah? Okay, so when you do the partial fraction, basically the AS, yeah, will be A over S plus 1 plus B over 2S plus 10. Okay, so you can work out for that, yeah, in which supposedly you're going to get this as equals to negative half of S plus 1 for the A, and for the B, if not mistaken, it should be equals to 4 or 2, yeah. So you're going to have 2 over 2S plus 10, yeah, 2S plus 10. Okay, so this can be cancelled out, yeah, can be simplified. We're going to have AS equals to negative 1 over 2 S plus 1 plus 1 over S plus 5. So we can now proceed with the inverse Laplace transform. We're going to have AT shall be equals to negative 1 over 2 exponential negative t of ut, okay, plus exponential of negative 5t of ut. So that should be your AT in time domain, yeah? Okay, any questions on these properties of different integration? Okay, there's no questions. I think we can proceed. All right, this is the example for this particular case. Basically, we want to test you on the partial fraction, yeah, partial fraction, and then we do the inverse of Laplace transform to find the YT. And I think that you can try to solve this on your own because the method is similar to what I've shown you in the previous slides. Yeah, so try to solve this. If you face any problems, you can always contact me, or you can always PM me to test. I mean to ensure the results, the answer that you get. Yeah. Okay. So let us proceed with the next properties. So that will be the properties of initial value theorem and the final value theorem, and this will be the last properties for the Laplace transformation. Okay, what is meant by initial value theorem and final value theorem? Yeah. Okay, it's stated here that if we have ft in time domain, yeah. Okay, so we can actually, sorry. Okay, we can see that if we have, um, if we put the limit of this t to be approaching 0, yeah, so this becomes f0, yeah, it becomes f0, okay. So the Laplace transform for this f0 will be equals to the limit of s approaching infinite of sfs. Okay, so that is why we call this as initial value theorem, because by this method we can find what is the value of f0 by simply testing or evaluating the limit of sfs. Yeah, so I repeat again. By using this initial value theorem, we can use it to find the value of f0, which is the value of ft time domain when t equal to 0 by simply evaluating the limit of s approaching infinite of ds multiplied with fs. Okay, and the same things apply for the final value theorem, in which, if we based on this equation, we can write this as the function of time when it is approaching infinite, or simply f infinite, in which the f infinite can be obtained by evaluating the fs, yeah, multiply with s, and we put that the s is equals to 0. Okay, so by substituting s equal to 0 for these terms, we can then obtain the value of f infinite. Okay, so that is why we call this as initial value theorem and this as final value theorem. Yeah, hopefully you understand this concept. So we're going to test this. We're going to ensure that our understanding by doing these examples here. Yeah? Okay, so we are given this example in which we are given the function of xs, yeah, xs in s domain. We have these terms, numerator and denominator. So the question is, we need to obtain what should be the initial value and final value for the time domain. Means that we need to find what is the x0, and this is to find what should be the x infinite. Okay, yeah, so got the point there. Okay, so based on this, to find the x0, we can use the initial value theorem just now, if we refer to the previous slide. So again, we can use this initial value theorem, which states that we can find the x0 by simply putting the limit of s approaching 0 of s of xs. Okay, so for this, we can write that s, so xs is here, so which is 2s squared plus 5s plus 12 divided by s squared plus 2s plus 10, okay, s plus 2. Okay, so we can take out the s power of 3, sorry, s power of 2 from the numerator. So we can have it as s power of 3. Okay, so 2s, sorry, I apologize, not 2s, it's only 2. Okay, going to have 2. Okay, going to have 2 there, plus 5 over s, okay, plus 12 over s squared. Okay, got the point there. And we divide it with this. We can take out the s power of 3 from the denominator. So we can have it as 1 plus, this is s power of 3, yeah? S power of 3, 1 plus 2 over s plus 10 over s squared. And that will be 1 plus 2 over s. Okay. So you can see the difference now, yeah? Okay. So that will be this s of xs, yeah? So we can cancel the s3, right? And now we can put the limit now. Yeah, we can substitute s equals to 0 in this equation. So when we substitute, sorry, not s, no, this is s approaching infinite. I apologize, yeah? S approaching infinite, not s0, but approaching infinite. So now we need to substitute all the s terms to be infinite. So that will be 0. So that will be 0, and all of this will be 0, yeah? So we left only with what? We left only with 2 divided by 1, so that should be equals to 2. So which means that x0 is equals to 2. Yeah, so for the xx given here, yeah, xs given here, the value of x0 in time domain, yeah, in time domain, the x0 or the initial value shall be equals to 2. Okay. You can testify this, you can prove this by what you have to do is that you have to do the inverse of Laplace transform, find the xt, and then you substitute. Once you have the xt, you substitute t equals to 0, and you can then obtain that the x0 is same as 2. Yeah, so this is the shortcut method to find the initial value for the given xs, yeah, the initial value in time domain for the given xs. Yeah, all right, yeah, hopefully you understand this concept clearly. Right, so I'm now going to proceed with the final value theorem to find the x infinite. So I'm going to rub this. Okay, sorry for that. Yeah, oh, I can just use this one. Okay, so now for the fundamental theorem, which is x infinite, yeah, this is the one, x infinite. So from the fundamental theorem, it states that x infinite is equals to the limit of s approaching 0 of s of xs. Yeah, this is from the fundamental theorem. And as such, when we try to solve for this, okay, the s, so we can take out the, we can write the xs here. So 2s squared plus 5s plus 12 divided by s squared plus 2s plus 10, okay, s plus 2. Okay, when we substitute all the s equal to 0 in this particular case, or in this particular terms here, so basically you're going to get that the value for that will be equals to 0, which means that x infinite, or the final value for the xt, yeah, will be equals to 0. Okay, right, so this is what we call as the properties of initial value and the final value theorem. Okay, any questions for these properties? So I can see that this is a shortcut method to find the initial value, or to find the xt, yeah, xt for the case of x0 and x infinite. So for the x0, you can use the initial value theorem, okay, and for the
Doctor,
x, yeah, yes,
when
yes,
when we use 0 instead of s, the answer is not going to be 0.
for this particular case, is it? Are you
Yes,
sure?
because
Okay,
the it's going to be 12 divided by 20.
okay, but we have has here, right?
Oh, okay, okay.
Okay, then. Okay. Okay, so for this x infinite, you're going to have final value theorem. Yeah, so this is a shortcut method to find the value of x0 and the x infinite. Yeah, without need to do the inverse of Laplace, we can get the xt, and once we get the xt, we can find the x0 and x infinite. So this is a very long method, a long way to find the x0 or x infinite. So instead, we can simply use this theorem to find both, yeah, x0 or and x infinite. Yeah. Okay, so let's have a look at this example. So we have this example, two signals given, where we have the xt and we have the yt. So xt is given to be t of ut. This is one, yeah, t of ut, while the yt is exponential negative 5t of ut, right? Yt is from 0 to 1. Okay. So you need to find the zt, in which zt is xt plus yt for the first question, and the second question, zt is x2t minus 1. So which means that for the second case is the xt which experience a time transformation. Yeah. Okay, so let us proceed one by one. For the first case here, okay, for the first case, number one, okay, for number one, we know that the xt is given by tut, yeah, So xt is given by tut. The Laplace transform for the xt will be the xs, and that should be equals to 1 over s squared, right? Whereas for the yt, which is exponential negative 5 tut, the Laplace transform for this yt shall be equals to 1 over s plus 5, yeah? Okay, so simply the Laplace transform for this zt, Laplace, which is zs, will be just a summation of the Laplace transformation for each of it. So you're going to have 1 over s squared plus 1 over s plus 5. This is the properties of subtraction and addition that we have learned in early parts of lecture 14. Okay, so that's the answer for the first part of this questions A. Yeah? Okay, for questions number 2, okay, for question number 2, which is the xt, which experience a time transformation. So we know that from the xt, yeah, the Laplace for that will be equals to, yeah, xs will be equals to 1 over s squared. Okay, so when we have xt minus 1, the Laplace for it will be equals to 1 over s squared e of negative s, correct? Okay, and then when we have a scaling of time, 1 over 2t minus 1. So from this, we can simply write it as 1 over 2. Okay, and then we're going to have 1 over s divided by 2 squared. Okay, exponential of negative s divided by 2. So that should be your Laplace transformation, in which we can simply rewrite it to be 2 over s squared exponential negative s over 2. Okay, so that should be the Laplace transformation for the second zt, which is the xt that experiences a scaling of time and also a shifting of time. Okay, any question for this question part A of this example? Is it understood? Okay, lah, hopefully you understand that, because there is no response. I believe that you understand it clearly, hopefully. Okay, so I'm going to delete this, yeah, because I'm going to proceed with part B of the questions. Okay. Okay, so for the part B of the questions, we have we need to solve a differential equation using Laplace transform method, in which we are given that initial condition v0 is negative 5. So we are given this equation, yeah, v prime minus 2v equals to exponential of 3t. So need to solve for this equation, means we need to find what should be the vt, yeah, what should be the vt. Right, so let us proceed with the solutions of this example. Okay, so we know that from v prime minus 2v equals to exponential of 3t, what you have to do is that you have to write this in Laplace transformation. So we are going to have s of vs. I'm using the differentiation properties, yeah, first order, minus v0. Okay, that should be the Laplace for the first terms here, v prime. The second term, it should be simply minus 2 of vs. Okay, and equals to, for the third terms here, it should be equals to 1 over s minus 3, yeah? Okay, we can substitute now the v0, which is negative 5. So for that, we're going to have vs. Okay, so that should be equals to s plus minus 2, sorry, minus 2. And for that, we're going to have 5, yeah, plus 5 equals to 1 over s minus 3. And if we rearrange this equation, we're going to have vs shall be equals to 1 over s minus 3 minus 5 divided by s minus 2. Okay, so I'm going to bring it here, and your vs can be further written to be okay, I'm going to have it as 16 minus 5s divided by s minus 3, okay, and that should be s minus 2. Right, so that should be your Vs in terms of S domain. Okay, so what we have to do now is that you need to do the inverse Laplace transform, but before we can do that, you need to proceed first with the partial fraction, okay, in which we can write this Vs as equals to A over S minus 3 plus B over S minus 2. Okay, so you need to find the A and B, and subsequently you can do the inverse of Laplace to find the Vt accordingly. Okay, so I leave this for you to solve this on your own, yeah? Because I believe that transformation from these terms to partial fraction can be very easy for you. Okay, and I believe that once you have A and B, you can simply find the inverse of Laplace transform for these two terms here, yeah? Okay, so I think we have done with these examples on this page, yeah? Okay, let us proceed further with this example. Am I too fast for you? Is it too fast, my teaching today? Is it okay? Is it okay the pace of teaching for today's lecture? I'm afraid that I'm too fast. So hopefully it's okay, yeah? Okay, good. Okay, let us proceed with examples here. So we are given two signals in this example. Okay, so for information, this is a sample of test questions on Laplace transform. Yeah, test two questions last time. So we are given Wt and we are given the Yt as the input to the systems in this diagram. Okay, Wt is having a delay by 3 seconds, and we are going to have the x1t. So x1t shall be then multiplied or mixed with the Yt in this diagram, and that will then give us the x2t. Yeah, and x2t will be integrated. Yeah, it pass through the integration block, and we're going to have the zt. Okay, so that is the block diagram for this example, and that should be the signals of in time domain Wt and Yt given this particular problems. Yeah. Okay. The first question is write the equation of Wt and Yt in the form of step unit. I think you can try to do this on your own. Yeah. I think you have learned this very much in chapter 1. Yeah, and also you have been tested in the test 1. So hopefully there should be no problems at all, yeah, to write the equation, to write the both signals Wt and Yt in the form of step unit. So I don't want to proceed with that, yeah. Okay, but for the Wt, we need to write it actually because it will be used later on. The Wt, if you base on this, it will be written as, yeah, in time domain, Wt shall be equals to 3t of ut. Okay, so that should be your Wt, yeah, in time domain, yeah. Wt, it will be 3t multiplied with the ut. Okay, then we need to find the Laplace transform for Wt and Yt. Okay, it seems that we also need to write this in terms of the step functions, yeah, because you need to find Laplace for that. So how is it? Let me see. So okay lah. So we need to write lah, yeah. Will takes a long time for us. Can I just provide you with the answer for that? Hopefully it's okay lah, yeah. Okay. So for the Yt, when you work out for the Yt, okay, you can try to work out on your own. You are going to get the Yt shall be equals to 2t of ut, okay, and that will be minus 2t minus 1 ut minus 1, okay, plus 2 ut minus 1 minus 2 ut minus 2. Okay. Okay, never mind lah. I'm going to cover this in detail on this particular transformation. So allow me to use a PowerPoint, yeah. Allow me to use the PowerPoint. I'm going to change the sorry for that. Let me see the PowerPoint. For that, yeah. Okay. Right. So I'm using a Word file. Okay. So if we can recall your diagram for the YT just now. Okay, for the WT should be okay, yeah. WT is known to be 3t of UT, comes from the diagram itself, yeah. But for the YT, if we can draw it back, so we're going to have the function which look like this. Okay, going to have this is the one, okay. Okay, so we have 2, this is 4, this is 1, this is 2, and there should be 3 lah. Okay. Okay, so from this YT, okay, we can write that YT shall be equals to, okay, this is a ramp, so that should be having a slope of 2. So that should be 2t, and it's between t minus ut minus 1. Okay, that should be for the first one. For the second one, between 1 and 2, that should be 4 of ut minus 1 minus ut minus 2. Okay. Okay, and then for the third, which is from 2 onwards, that should be equals to 2 ut minus 2, yeah? Okay, so you got the point there. Right, so now we're going to proceed with this yt. So we can write it as 2t of ut, okay, minus 2t of ut minus 1, okay, plus 4 of ut minus 1, okay, minus 4 of ut minus 2, then plus 2 of ut minus 2. Okay, then if we proceed further, we can write it as 2t of ut plus negative 2t plus 4. Okay, we got the same terms for ut minus 1. We're going to have these terms, right? Okay, and then we're going to have a negative 2 of ut minus 2. Okay, so we can now write further as 2t ut. Okay, so I can take out 2 from these terms here. We're going to have negative 2 of t minus 2 ut minus 1 minus 2 ut minus 2, yeah? Okay, so we're going to have 2t of ut minus, okay, so note that this is ut minus 1, but here is t minus 2. So we need to write this as t minus 1, same as this, yeah? So you need to be very clear on that, yeah? So what we can write is that we're going to have 2t minus 1 minus 1, ut minus 1, minus 2 ut minus 2. Okay, so get the point there, yeah? We're going to have 2t of ut minus 2t minus 1 ut minus 1 plus 2 ut minus 1 minus 2 ut minus 2. Okay, so you got the point there, understand? So from these terms here, you can now have 2 terms, which is the first one is negative t, 2t minus 1 ut minus 1, plus the second term is 2 ut minus 1, which we are we are actually factor out, yeah, factor out these terms number 2 over there. Okay then. Okay, so once we have this, we can simply do the Laplace transformation as requested on the question. So that will be 2 over s squared. The second terms here will be negative 2 over s squared e negative s. The third terms will be plus 2 over s exponential negative s. And for the fourth terms here will be negative 2 over s exponential negative 2s. So that should be your Laplace transformation for signal yt. Okay, is it clear? Hopefully it's clear, yeah? Okay, so I'm now going to share uh, the PDF file now. Okay, sorry, lecture 14. Okay, we get back to these questions. Okay, so we have obtained the Laplace transform for Wt and Yt successfully. Okay, so the third question is need to find out what should be the Zt in the S domain. Yeah, what should be the Zt in the S domain? Okay, so from this figure, we know that your x1t, yeah, x1t is equal to Wt minus 3, yeah, and delayed by 3 seconds. So x1t x1t shall be equals to Wt minus 3. Okay, yeah, in which you're going to have the equation in time domain should be 3t minus 3 of ut minus 3, because previously we know that Wt is 3t ut, right? So when we delay by 3 seconds, it should be 3t minus 3 ut minus 3. So that should be the x1t lah, yeah. Okay, and we know that now we can write that the x1t, yeah, x1t can be in terms of the figure. Yeah, in terms of the figure, we can have the pattern should be look like this, shifting by 3 units. Yeah, 3 units to the right. Okay, so that should be your x1t. Okay, so x1t is said to be, okay, so I label this x1t. So x1t, this is 0, and then we have a ramp, x1t. So x1t is said to be multiplied with the yt. So means that this function x1t is multiplied with the yt here. So if I can rewrite or redraw the x1t in this yt signal, so my x1t should be look like this. So this is my x1t. Am I right? So when we multiply x1t and yt, your portion that will be that shall be remain only will be this part, which is for time t bigger than 3, because everything below than 3 shall be equals to 0. Yeah, shall be equals to 0. So for this particular case, we can write that the x to t, which is a multiplication of x1t and yt. Yeah, I can rewrite here x1t multiply with yt. Okay, because this is 3 minus 3 ut minus 3, while for yt, for time t bigger than 3, the amplitude is 2. Okay, so when you multiply these two terms here, your answer will be 6 of 3t minus 3 ut minus 3. So that should be your x to t, yeah? The result of multiplication between the x1t and yt, which is applicable only for time t bigger than 3. Right. Okay, hopefully you understand this, yeah? Right, so from this particular case, we can do the Laplace transformation for the x to t. So Laplace for that will be equals to 6 over s squared exponential of negative 3s, yeah? So this will be the Laplace transform for the x to s. Okay, if we base on this diagram, we know that the zt is the result of the integration of the x2, right? Which means that we can write that the zs basically is the x2s divided by s. Okay, if I can write that in terms of a time domain, zt equals to integration of xt dt. 0 to t lah, yeah, dt. So in terms of Laplace transform, we can write this as zs is equals to x2s. This is x to t, yeah, x to t. So zs is equals to x2s divided by s. So you can see, yeah, this is from the diagram. So I rewrite in terms of the equation. So zt equals to integration from 0 to t of x to t dt. So when we do the Laplace transformation, the zs will be x to s divided by s. So we have obtained the x to s previously. So simply we just divide by s, and we're going to have 6 over s power of 3 of exponential negative 3s. So that should be our zs. So we have obtained the zt in terms of the f domain by simply divided the x to s that we've obtained previously with the s term. So that should be your zs. Yeah. So this is the zs, which is the zt in the s domain. Okay, is it clear on the solution for this example? Any questions so far? This example? No questions at all? Okay. So if there's no questions, I think I'm going to stop here. Okay. So tomorrow's class, we're going to proceed with the rest of this lecture 14. I think we have few examples to be solved. Okay. Is there any more questions? Okay, that's all. Yeah, we have done with lecture 14. Okay, so that's the end. That should be the last examples for lecture 14. Okay, so I hope by this lecture 14, by these few examples, you have good understanding on the properties of Laplace transform. Okay, and you must be able to solve a few properties of Laplace transform. Okay, and this will be tested later when we do the tutorial, yeah, for chapter 4. Okay, and for tomorrow's class, we're going to proceed with lecture 15, yeah, in which we're going to learn about the application of Laplace transform in solving the circuit analysis problem. Okay then? All right. Okay, so I think I have to sign off now. Okay. Okay, any questions?
Can you share the QR code?
Okay, the QR code. Okay, sure. Okay, I think that's all. And thank you for attending the class. We're going to meet you again tomorrow. Yeah, lecture 15. Yeah. Okay, thank you very much. See you again tomorrow at 11. So I'm going to share again the QR code. Yeah.
Okay, thank you, Doctor.
Thank you. Welcome. Bye bye.